50 million years ago, Earth looked nothing like the planet we know. Antarctica wasn't a frozen desert. It was a rainforest. Palm trees swayed where glaciers now tower, and crocodiles glided through rivers shaded by ferns. Across the Arctic, Alaska's coasts were lined with mangroves, not ice floes. From pole to pole, the planet shimmered green, wrapped in humidity and heat. There was no ice anywhere. Not a single glacier, not even at the poles. The seas were 60 meters higher, swallowing coastlines and turning continents into chains of islands. And in these tropical oceans, monstrous predators ruled. Whales with jaws like saws, snakes longer than buses, and sharks the size of submarines. This was the last time Earth was completely iceless. A world so hot, it nearly burned itself alive. And if the scientists are right, we're not heading toward it. We're racing back to it. To understand this forgotten age, we have to travel back to the Eocene Epoch, between 56 and 34 million years ago, a time when the planet ran on fire and carbon. Volcanic chains in the North Atlantic unleashed colossal eruptions, pouring billions of tons of carbon dioxide into the atmosphere. As the gas thickened the sky, the world entered a greenhouse state unlike anything seen since the age of dinosaurs. CO2 levels soared above 1,200 parts per million, nearly 3 times higher than today. Global temperatures averaged around 28 degrees Celsius, while the polar oceans lingered at a balmy 12 degrees. There were no permanent ice caps. The air was heavy with moisture. Storms were violent and frequent, and coastlines vanished beneath swollen seas that lapped at the edges of the continents. Yet in this furnace, life didn't die. It thrived. Tropical forests covered Antarctica, where crocodiles and turtles shared the rivers. Early primates swung through North American jungles. Giant plant-eating mammals shaped landscapes that never knew snow. Earth's ecosystems were vast, humid, and alive in ways modern science is still piecing together. But this paradise carried a flaw. It was built on instability. Beneath its surface, tectonic plates were shifting, ocean currents were changing, and the planet's chemistry was beginning to betray it. The warmth that had nurtured life was slowly setting the stage for an extinction. Before we uncover that rise and fall, make sure you're subscribed to Beyond Extinction, where we bring lost worlds back to life and reveal the deep time stories still written in our planet's bones. The Eocene wasn't simply a warm age. It was the peak of a planetary fever. It began in fire. Around 56 million years ago, at the boundary between the Paleocene and Eocene epochs, something extraordinary happened. The Paleocene-Eocene Thermal Maximum, a pulse of heat so intense that global temperatures spiked by at least 5 to 8 degrees Celsius in less than 20,000 years. The cause lay in the depths of the Earth. Immense volcanic eruptions tore through the crust of what is now the North Atlantic igneous province, spanning from Greenland to northern Europe. These eruptions released trillions of tons of carbon dioxide and methane, triggering a chain reaction that trapped heat in the atmosphere. It was as if the planet had exhaled carbon and forgotten how to breathe it back in. For hundreds of thousands of years, this greenhouse engine kept running. Carbon dioxide levels soared to between 1,200 and 1,500 parts per million, roughly triple modern values. With that came a greenhouse climate system so efficient that average global temperatures climbed to nearly 28 degrees Celsius, and even the polar oceans held steady at a mild 10 to 12 degrees. The sea became a thermal bath, a worldwide incubator for life. But there was more at play than just carbon. Earth's geography made the heat inescapable. Antarctica remained connected to Australia and South America, forming a single supercontinental loop that prevented the birth of any cold southern current. Without an oceanic conveyor to carry heat away, warm tropical waters spread evenly around the globe. Atmospheric circulation shifted too. Jet streams weakened, monsoons grew stronger, and rain fell across what would one day become the Sahara and Arabian deserts. Scientists have reconstructed this world through oxygen isotopes preserved in the shells of foraminifera, microscopic plankton that record temperature like tiny thermometers. Those isotopes tell us that sea levels were 60 to 70 meters higher than today, flooding entire continents and turning mountains into islands. In this steamy world, the Earth's climate acted like a single, interconnected system, oceans and forests feeding each other in a cycle of endless humidity. Forests reached the poles, jungles spread across continents, and tropical storms the size of modern hurricanes raged without pause. But this balance was a tightrope. Beneath all the abundance, the planet's chemistry was already shifting. Volcanoes cooled, carbon drawdown from silicate weathering increased, and deep in the Southern Ocean, tectonic plates were slowly rearranging. Nature had built the most vibrant greenhouse in history, and it was already laying the foundations for its collapse. If you had stood in Antarctica during the height of the Eocene, you wouldn't have seen a frozen desert. You would have seen a paradise. Fossil beds on Seymour Island and the Antarctic Peninsula reveal entire forests of Nothofagus, Araucaria, and Podocarpus, trees that today only grow in the temperate zones of the southern hemisphere. Their trunks were ringed with moss, ferns, and fungi, while vines climbed toward a pale sky filtered through endless mist. Even in winter, when the sun vanished for months, the ground never froze. Leaves continued to photosynthesize through twilight, nourished by long seasons of rain. Crocodiles and freshwater turtles prowled slow-moving rivers that wound through the greenery, and tiny marsupials, relatives of modern opossums, nested among the roots of ancient beaches. There was no ice, no snow, no silence, only the constant rhythm of life. Far to the north, in what's now Alaska and the Canadian Arctic, similar forests thrived under a midnight sun. Fossils from the Ellesmere Island formations show palm pollen, cypress, and dawn redwoods. Insects flitted between broad leaves, their delicate wings preserved in amber. Even at 70 degrees north latitude, average temperatures stayed above freezing all year. The Arctic Circle was no tundra. It was a swamp. This band of life stretching across the planet formed what scientists call the Eocene rainbelt, a continuous green corridor that encircled the Earth. Storm systems migrated north and south with the seasons, feeding an atmosphere heavy with moisture. The air smelled of resin and rain, and the soil steamed with decay. Within these forests, mammals were diversifying rapidly. Tiny adapiform primates, early relatives of lemurs, leapt from branch to branch in search of fruit and insects. Bats, among the earliest true flyers, hunted under the canopy. Rodents scurried across leaf litter, and early ungulates grazed in the meadows between forests. The continents teemed with species that had only just begun to explore their evolutionary potential. But the Eocene world wasn't just lush, it was unpredictable. With carbon levels this high, weather patterns were chaotic. Regions alternated between torrential floods and long droughts. Fires swept through forests in seasonal cycles, their charcoal layers now visible in fossilized sediments. The combination of warmth, rain, and lightning created perfect conditions for destruction and renewal. Still, life adapted to every challenge. Ecosystems evolved quickly, filling every niche that warmth could offer, from the depths of flooded jungles to the coasts of expanding inland seas. The Earth had become one enormous greenhouse laboratory, experimenting with life in forms both familiar and alien. Before we dive into the oceans ruled by prehistoric giants, tell me, if you could step into one of these ancient worlds, would you explore the rainforest or risk the deep? Drop your pick in the comments. I want to see who's brave enough for the Eocene seas. Yet, even in this golden age of abundance, the oceans were already changing. Beneath the calm green surface of this world's forests, vast predators had begun to rise from the sea, and the balance of life was about to tilt toward the deep. If the land was a paradise, the oceans of the Eocene were an empire of killers. With no polar ice to lock water away, The seas had risen higher than at any time since the age of dinosaurs. Shallow, sun-warmed waters stretched over entire continents. Florida, Denmark, and the Sahara Basin were flooded into archipelagos. It was in these drowned worlds that the most terrifying hunters Earth had ever seen began to thrive. The kings of these seas were the Basilosaurids, the first whales to rule the planet. Unlike the gentle baleen giants of today, these were fast, muscular carnivores that hunted anything large enough to bite. Their name means king lizard, a fitting mistake, because early fossil hunters thought they were marine reptiles. In truth, they were mammals, apex predators that turned the ocean into their dominion. The most famous of them, Basilosaurus icis, stretched to nearly 18 meters long and weighed around 15 tons. Its skull, over a meter in length, held a battery of sharp conical teeth designed to puncture and tear flesh. With a bite force of nearly 20,000 newtons, it could crush the ribs of a whale in seconds. Fossils from Egypt's Wadi al-Hitan, the Valley of Whales, tell a gruesome story. In the fossilized stomachs of some Basilosaurus skeletons lie the bones of smaller whales, especially Dorodon atrox, a 5-meter-long relative. The evidence is clear. These whales preyed on their own kind. But Basilosaurus wasn't alone. The family it belonged to, the Basilosauridae, was diverse and global. In Egypt's deserts, scientists have unearthed the agile Dorodon, built for pursuit and capable of sharp turns. In Peru, the newly described Paracetus colossus astonished researchers with its sheer weight. Its bones so dense that they suggest a creature over 20 meters long and weighing up to 50 tons. Unlike its hunting cousins, Paracetus was slow and likely fed near the seafloor, scraping mollusks and crustaceans from sediment. Smaller basilosaurids like Tautus, named after King Tut, still dwarfed most modern sharks, reaching over 8 feet and filling the role of mid-sized hunters. In life, they formed a food web of whales hunting whales, a chain of predation unknown in any other epoch. The seas, however, belonged to more than whales. Alongside them swam the early titans of another dynasty, the Otodus sharks, ancestors of the megalodon. The species Otodus auriculatus reached 9 to 10 meters long, about the size of a large killer whale. Their even larger cousin, Otodus obliquus, sometimes reached 12 meters, making it one of the biggest sharks of all time. Their teeth, broad, triangular blades serrated along the edges, tell a tale of ferocity. Fossils of Otodus teeth have been found from North America to Morocco to Antarctica, proving their dominion over the global seas. A single shark could lose and replace over 20,000 teeth in its lifetime, a constant rain of ivory over the ocean floor. And if sharks and whales weren't enough, the Eocene had its serpents too. The Paleophydae, an extinct family of marine snakes, reached lengths that defy imagination. The largest, Paleophis colossius, could exceed 12 meters, nearly as long as a bus, and rivaled the prehistoric Titanoboa in scale. Others, like Paleophis terris, were smaller at around 5 to 6 meters, but faster and more agile. These snakes had flattened tails and robust spines built for power, not speed. They were ambush predators, relying on stealth in shallow seas, striking at fish, sharks, and perhaps even small whales. Their vertebrate fossils have been found across Europe, Africa, and North America, tracing a tropical distribution that mirrors their prey. Along the coasts lived another lineage, still in transition, the Protocetids, or early amphibious whales. One of them, Paragocetus pacificus, discovered in Peru, could walk on land and swim in the ocean. It had webbed feet, strong legs, and a tail made for propulsion, a true half-step between land mammals and marine hunters. On nearby shores, early Sirenians, primitive relatives of today's manatees and dugongs, fed lazily on seagrasses and mangroves, still bearing finger bones inside their flippers, a sign of their terrestrial ancestry. From apex predators to gentle grazers, the Eocene oceans were a gallery of evolution's experiments. Every ecological niche was filled, from the surface, where Basilosaurus reigned, to the depths, where Paracetus lumbered, and along the coasts, where amphibious whales still tested their limbs against the tide. But this watery paradise was not stable. Beneath the tranquil waves, deep ocean currents were beginning to shift. Carbon was slowly being drawn from the sky, buried in the seafloor as plankton died and sank. The ocean that had given life to monsters was quietly engineering their extinction. The greenhouse world had reached its peak, and just as it had begun, in fire and upheaval, it would soon end in cold and silence. While predators ruled the oceans, the land was no less astonishing. The Eocene was an age when the air itself seemed to feed growth. Warm, carbon-rich, and heavy with moisture, it turned continents into sprawling hothouses teeming with strange, oversized life. Forests blanketed nearly every region of the world, from equatorial lowlands to the edges of the poles. Towering over these jungles were the brontotheres, sometimes called thunder beasts. They looked like prehistoric rhinos, but were their own unique branch of mammals. The largest species could exceed 4 tons in weight and stand nearly 3 meters tall at the shoulder. Their skulls bore paired bony horns, not made of keratin like modern rhinos, but extensions of the skull itself, possibly used for dueling or display. In the steamy Eocene heat, herds of brontotheres moved through forests of giant ferns and cycads, cracking branches underfoot and sending birds scattering through the canopy. They were joined by the embrithopods, heavy-bodied herbivores that resembled elephants, yet were more closely related to sea cows. Fossils of Arsinoitherium, a massive embrythopod from Egypt, reveal a creature over 4.5 tons in weight, armed with twin conical horns and thick legs built for supporting bulk. Alongside them wandered the early proboscideans, like Moratherium, which resembled a hippo-sized tapir. It wallowed in marshes, grazing on soft vegetation and using a short trunk to pluck leaves. These great browsers shared the forests with primates, bats, rodents, and small carnivores. Early lemur-like primates, such as Notharctus, leapt between branches, while fruit bats and insectivorous bats hunted beneath the canopy. Forests of broad-leaved trees hummed with life, pollinating insects, croaking amphibians, and songbirds whose descendants would one day spread across the globe. But even paradise had predators. The hyenodonts were among the most fearsome, long-skulled beasts with jaws that could open nearly 150 degrees. Some species rivaled modern lions in size, with teeth shaped for slicing flesh. Alongside them were the nimravids, also known as false saber-tooths. One genus, Hoplophonius, had elongated canines and muscular forelimbs, perfect for ambushing prey in dense forest. They were early prototypes of the big cats to come, their power echoing through future ages. Reptiles too refused to fade away quietly. On the warm continents of South America and Africa, the Basilosaurus, a family of terrestrial crocodile-like predators, rose to dominate. Unlike modern crocodiles, they had long legs and upright gaits, chasing down prey on land. One species, Barinasuchus, could reach 10 meters in length and 2 tons in weight. Its blade-like serrated teeth tore through flesh rather than gripping it. In the Eocene, crocodilomorphs didn't wait at riverbanks. They hunted across the plains. This was a world where mammals and reptiles shared power. Giant birds, some over 2 meters tall, stalked open clearings, snapping bones with hooked beaks. Forests were alive with tension. Herds trampling ferns below, predators lurking in the shadows above. Yet beneath all this abundance, subtle cracks were forming. The same geological drift that had once spread warmth across the globe was about to reverse the flow. The first hints of chill were coming from the south, and they would rewrite everything. Around 34 million years ago, the balance broke. What had been a stable, steamy planet began to cool, and it started with Antarctica. For tens of millions of years, the southern continent had been lush and green, still tethered to Australia and South America by fragments of land and shallow seas. But tectonic plates never stopped moving. Slowly, the last connections snapped. opening two new ocean corridors: the Tasmanian Gateway between Antarctica and Australia, and the Drake Passage between Antarctica and South America. Through these narrow channels, cold currents began to circulate freely. They merged into a continuous band of water that circled Antarctica, the Antarctic Circumpolar Current. This current insulated the continent from warm equatorial seas, trapping cold around the pole and preventing heat from returning south. It was the moment the world's thermostat flipped. As the current strengthened, temperatures plunged. Atmospheric carbon dioxide fell below 750 parts per million, perhaps as silicate weathering and new mountain ranges, like the Himalayas, sucked carbon from the air. Global averages dropped by more than 6 degrees Celsius, and the planet's first true ice sheets began to form. In Antarctica, the transformation was visible. Snow that once melted into rivers began to linger through summer. Thin layers of frost grew into glaciers that crept down mountainsides. Within a few 100,000 years, a continent that had been a rainforest was sealed under ice. Sea levels fell by over 60 meters as water locked into ice caps. Warm coastal seas retreated, exposing new land across Africa, Asia, and the Americas. Forests shrank and fragmented. The humid jungles of the Eocene thinned into open woodlands and grasslands. Global rainfall patterns changed. Once wet regions grew dry, and vast monsoon systems collapsed. The oceans felt it first. Currents reversed, bringing oxygen-rich waters into the deep sea and changing the chemistry of marine ecosystems. Phytoplankton, once flourishing in warm shallows, began to decline. Coral reefs, adapted to stable warmth, faded into ghostly ruins. It was the dawn of a new world, one ruled not by heat and humidity, but by ice and adaptation. The greenhouse Earth had fallen. In its place was the planet we recognize today, one that breathes in cycles of warmth and frost. Yet for all its violence, this transformation wasn't an ending. It was a threshold, and on the other side waited evolution's next act: extinction and rebirth. The cooling did not come quietly. It was a global reckoning, a reshuffling of life on a scale unseen since the dinosaurs' fall. As temperatures dropped and sea levels fell, ecosystems that had thrived for millions of years began to crumble. Species vanished, not in a single cataclysm, but through a drawn-out sequence of collapses that unfolded over hundreds of thousands of years. In the oceans, the transformation was immediate and merciless. 20 to 35% of marine species disappeared, victims of cold, chemistry, and starvation. Warm water plankton, once the foundation of the food chain, declined by nearly 80%. As they vanished, the seas turned clearer, emptier, and less productive. Coral reefs, deprived of their symbiotic algae, bleached and broke apart. The shallow seas that had once teemed with predators became deserts of sand and silence. The Basilosaurids, apex whales of the Eocene, were among the first casualties. Their massive bodies and specialized diets left them helpless in cooler, less bountiful oceans. Fossils of Basilosaurus isis and Dorodon atrox vanished from the record by the early Oligocene, marking the end of a dynasty. The Otodus sharks, deprived of prey, began to dwindle as well, replaced by smaller, faster hunters, better suited to the colder seas. Even the colossal Paleophis sea snakes, adapted for warm shallows, could no longer survive in cooling waters. Along the coasts, the last of the protocetids, those amphibious whales that could still walk on land, disappeared, their transitional bodies outpaced by evolution. Only a few adaptable lineages, such as the early baleen whales and toothed dolphins, survived to inherit the oceans. On land, the upheaval was just as profound. The great rainforests that had covered the continents began to recede, replaced by open woodlands, savannas, and the first true grasslands. The change favored new kinds of herbivores, nimble grazers that could run rather than hide. From these survivors evolved the ancestors of modern horses, camels, and antelopes, mammals shaped by endurance rather than size. But many of the Eocene's giants could not adapt. The Brontotheres, dependent on lush vegetation, vanished entirely. The embrithopods, heavy and slow, followed them into extinction. Early primates, once so diverse in the warm forests, lost much of their range and retreated to the tropics. Even the predators that had once stalked them were not spared. The great hyenodonts and cebecosaurs, dominant for millions of years, dwindled until only their smaller, colder-adapted relatives survived. The cooling reshaped the face of the continents. Rivers cut through newly exposed plains. Dust storms swept across the interiors of Asia and North America. Seasonal extremes took hold. Cold winters, dry summers, short bursts of rain. The world that emerged was one of migration, hibernation, and adaptation, where only those who could change endured. Paleontologists call this transition the Eocene-Oligocene boundary, and though it ranks as a minor extinction event compared to the end of the dinosaurs, it changed everything. It ended the last truly tropical Earth and began the long, icy era we still live in today, the age of ice and mammals. And yet, in its quiet devastation, it also planted the seeds for evolution's next masterpieces. From the survivors of this chill would arise the elephants, whales, cats, and humans that would one day inherit a colder, leaner planet. If you lived during this turning point, when forests froze, seas withdrew, and the giants vanished, do you think your species would have made it? Tell me in the comments. Who would have adapted, and who wouldn't? When scientists drill into the seafloor or slice through layers of ancient rock, they're not just collecting fossils. They're reading time itself. In those strata, in the shells of microscopic organisms, lies a record of how the Earth once changed, and what happens when it does again. Those records show that during the Eocene, when carbon dioxide climbed past 1,000 parts per million, Earth crossed a threshold. Ice vanished, seas rose, and temperatures stabilized only after tens of thousands of years. The same concentration, scientists warn, could return by the year 2300 if modern emissions continue. But the key difference is speed. The Eocene's rise unfolded over millennia. Ours is happening in centuries. Back then, warmth came from volcanoes and tectonic shifts. Today, it comes from us. The rate of carbon increase in the Eocene was around 0.0001 parts per million per year. Today, it exceeds 2 parts per million annually, tens of thousands of times faster. In geological terms, we're a natural disaster unfolding in real time. The parallels are haunting. As temperatures rise, modern species are already reacting as their ancient counterparts did. Marine life migrates toward the poles. Coral reefs bleach in warming waters. Forests burn where rainforests once grew. Species that cannot move quickly enough face the same fate as the Brontosaurus and Basilosaurids did 34 million years ago. If all of Earth's modern ice melted, sea levels would rise by about 60 meters, flooding coastlines across every continent. Bangladesh, the Netherlands, southern China, Florida, and London would vanish beneath shallow seas. By Eocene standards, it would be a return to normal. But for us, it would be the end of civilization as we know it. The Eocene teaches that the planet always recovers, but never in time for the species that caused the change. The Earth will find a new balance. The question is whether we will be part of it. We are living through a moment that echoes the distant past, a brief replay of a story the planet has told before. When the air fills with carbon, the seas rise, and the ice retreats, the world does not end. It transforms. But transformation comes at a cost. And this time, the cost might be us. The last iceless Earth ended when Antarctica froze, and the feedback loop of cold and reflection locked the planet into the glacial rhythm we've known ever since. But nothing on Earth is permanent. In another 50 million years, Antarctica will drift north again. The circumpolar current will weaken, and the world may thaw into green once more. The difference is that we may not have to wait. The carbon we burn today is already waking ancient patterns from their sleep. The seas are rising, The poles are melting, and the Earth's great experiment with heat is beginning again. Only this time, its architects are us. The Eocene shows that warmth can be beautiful. It built forests on Antarctica and filled the seas with life. But it also shows that beauty is fragile. It can vanish in a geological heartbeat. The last time the world was iceless, it took nature millions of years to recover. Today, we may give it only centuries. Earth has lived without ice before. It will again. The real question isn't whether the planet can survive another greenhouse age. It's whether we can. If this journey through deep time changed how you see our planet, hit like and subscribe to Beyond Extinction, where we uncover the world's time forgot and the lessons they left behind.